Good afternoon, everyone. We are delighted to have you all today. We are the leadership board of the EMI Dynamics Technical Committee. Ahmed, would you like to say a few words?
Sure. Greetings, everyone. Thank you so much for joining us today online. We are happy to bring you another EMI Dynamics Committee seminar series. We have two wonderful speakers that will be introduced today. I would like to also remind everyone about the dynamic committee activities. We have a very wonderful website that is being maintained by Tisha. Thank you so much, Tisha, for all the hard work. We have several kind of dynamic committee activities, including the seminar series. If you're interested in attending the seminar series, please communicate with us, with the leadership team, and we'll be happy to basically help you schedule a seminar series. We have a mentoring program, which is a very exciting program, especially for junior faculties and researchers. If you want to connect to a senior member in the community and get guidance about your career path, that activity exists and we can support that. We are also sponsoring a student paper competition for this coming EMI in Anaheim. So if you are a student or you know of students who are willing to contribute to that competition, we have raised basically, I think, $1,500 for student paper competition prize. We'll also have an email communication process. If you sign up or if you would like to be a member, basically communicate with us. And if you are a member, you will receive emails from us, hopefully one or within the next few days, to provide some guidance about the student paper competition and so on. With that being said, I'm gonna basically cut it a little bit short and bring it back to Marianne to introduce our wonderful speakers for today.
Thank you so much for introducing our committee activities. We are delighted to have a wonderful list of speakers this year. And we have this morning or afternoon, wherever you are, Dr. Yanlin Guo, as well as Dr. Herta Montoya. So let's go ahead and get started. So as our wonderful speaker is sharing her slide presentation, let me talk to you about Dr. Yanlin Guo. She is an associate professor in the Department of Civil Environmental Engineering. She is currently the director of Center for Sustainable and Intelligent Transportation Systems at Colorado State University. Her research expertise lies in the areas of mitigation of wind and compound hazards in the built environment, real-time structural health monitoring, and data and physics integrated simulation and modeling of extreme wind and wind effects on structures. She's also experienced in remote sensing, computer vision, system ID, and structural dynamics, of course. And we are delighted to hear more about the work that she's been doing in uncrewed aircraft systems-enabled dynamic displacement measurement techniques. Without further ado, help me in welcoming our speaker. Thank you. And we'll wait until our next speaker finishes before we open it up for the audience to ask questions. So the structure is 25 minutes for the first speaker, 25 minutes for the next speaker, and then we'll have an opportunity to engage with both speakers. As you have questions, please put them on the chat so that we can address them at the end. Thank you, and I hope you enjoy this presentation.
Thanks for the introduction. Good morning and good afternoon, everyone, depending on where you are. I'm very glad to have this opportunity to share with you our recent work on dynamic displacement measurement using the UAS systems. So first, I will briefly introduce my motivation of doing this work, and then I'll introduce two techniques that we recently developed, and then I will conclude the presentation. So for the audience from the Dynamics Committee, we all know that the displacement measurement is very critical for structural health monitoring. However, the direct displacement measurement is challenging because it requires the reference. And the traditional contact sensors cumbersome to place, maintain, or relocate from logistics standpoint. In the past, actually, I had a chance to work with contact sensors for different long-term structure health monitoring systems. However, when I started my own research group, I found that it's very challenging to convince the owners to instrument the long-term health monitoring systems because of the cost and the logistics that involved. So I start thinking that what if we can provide more portable and flexible approaches to measure the dynamic displacement that can be carried to different types of structures. So that started my journey of investigating the UAS systems. So in this, we have done actually we tried several ways to do the dynamic displacement measurement. In this presentation, I'm going to present two techniques that we developed to measure three components of dynamic displacement, X, Y, and Z direction motion simultaneously. So the first technique, we use the UAS equipped with the Intel RealSense camera. As you can see, this is the model of the RealSense camera that we used in our study. This RealSense camera set includes two infrared cameras and also an infrared projector, as well as an optical camera. Infrared camera, and this sensor set actually is made for indoor use and short range. And then we put this sensor on the DJI Mavic 2 Pro UAS system because it's pretty stable during flight. As you can see, we use the infrared projector and infrared cameras to capture the in-depth motion of the structure. So for example, this is the camera. So this is the camera set and the relative motion between the object and the camera in Z direction. This is the in-depth direction. And then the infrared projector projects the speckle pattern on top of the structure. And this speckle pattern cannot be seen by the naked eyes, but it can be seen by the IR cameras. And then using the two cameras, we can do the triangulation to find out the depth direction motion. So this motion is the relative motion between the moving object and the camera set. However, the UAS itself also has some vertical motion. So to be able to compensate that, we also need to figure out the motion of the UAS itself by tracking a stationary target. And then using the summation of the UAS motion and the motion of the ROI with respect to the cameras, we can get the true motion of the object. So this is about the first component, Z direction component. Then we use the optical camera, which is the regular camera, to get the X and Y direction motion of the object. So in this technique, we use color path filter to increase the contrast of the target. And then we apply direct linear transformation and dimension mapping to get the displacement of the in-plane motion. So same deal as the previous scenario, the UAS will hover horizontally. So we also need to track the motion of the UAS itself. So we use a stationary target. And then this UAS image can see both the stationary target and the moving target. Then we can find out what is the motion of the UAS with respect to the reference target, and also what is the motion of the object with respect to the UAS system. Then we can recover the actual displacement of this object. Sorry. And by combining the depth direction measurement and in-plane direction measurement, we can simultaneously measure the three components of the dynamic displacement. So here's our experimental setup. We use a cantilever beam on a shake table. The shake table is moving in both X and Y directions with different frequencies. And then we flick the the free end of the cantilever to excite the vertical motion. And then this is the Mavic drone, and this is the RealSense camera. And on the tip of this cantilever, we also instrumented an accelerometer so that we can do some comparison. This slide shows the final result. So for the ground truth motion, which is excited by the shake table, we know what it is, and it is plotted by this dashed red line, as you can see here. So this figure is for X direction, this is for Y direction, this is for Z direction. And then the UAS measurement, you get two measurements. One is the relative motion between the object and the cameras. And the other is the relative motion between the UAS and the stationary target. By combining these two, we get the blue curve, which is the true motion of the object. As you can see, we had a pretty good match with respect to the ground truth for both X and Y direction. The frequency error is fairly small, and the mean absolute error for the displacement is in a couple of milliliters. And for Z direction, because we do not have the ground truth displacement measurement, so we compare the frequency and damping that we identified from the displacement we get from the cameras to the frequency and damping that we get from the acceleration data. And again, we see a fairly consistent agreement between the two. However, this experiment is conducted in an indoor environment with a small scale laboratory testing. So when we try to study if we can scale up this technology for full-scale application, we first studied the measurement accuracy. So what we found is that within a short distance between the cameras and the object, we get a fairly good accuracy for measurement. Actually, in our past experiment, the distance is about 0.75 meter. However, in the full-scale application, we typically will need the UAS to be further away from the structure. Let's say if we assume at least 5 meters is required, and then from this projection, you can see that when the distance goes beyond the 3.5 meters, the error is too large to be accepted. So that's one limitation of this application. And then also the RealSense sensor is designed for indoor implementation. If it's applied to the outdoor, the speckle pattern of the infrared projector will be washed out by the sunlight. So that's another condition that is not ideal for scaling up. The past example that we did, we used the reference target. In the practice, if we have to place targets to the structures, that create more logistics issues. So we prefer not to use the target in the full-scale applications. So in light of this limitations, we're thinking about other ways to scale up the 3C dynamic measurement using the UAS system. That motivated us to develop the second technique, where we instrument the UAS system with the dual stereo camera pairs. So in this implementation, we have two pairs of stereo vision cameras. One pair, as you can see here, is looking at a stationary reference to get the UAS motion. And then there is another pair of the camera, as you can see here, or from the side view. This pair is looking at the moving object. So total, we have 4 cameras. And the camera that is looking at the moving object, we refer them to the ROI cameras, region of interest cameras. And then the camera that is looking at the stationary reference, we refer them to as the REF cameras, reference cameras. So there are several challenges with this new implementation. The first challenge is the dual stereo variant calibration. Although the stereo variant calibration is mature in the literature and in practice. However, in our specific scenario, the two pairs of the cameras are looking at actually perpendicular directions. So the two pairs cannot see the same target. That makes the calibration very challenging. There's no existing ways algorithms to do that. And then the second challenge is that since we want to scale up this application, we're using a larger drone platform. And the larger drone platform not only have the 3 translational motion, but it also has the rotational motion. So we essentially need to compensate all 6 degrees of freedom of the US movement. And also we need to consider some practical needs. For example, we like to increase the working distance between the camera and the object. We like to be able to utilize the natural features of the object. Also, we don't want the technique to be picky about lighting conditions. We want the technique to be more versatile at different lighting conditions. So with all that in mind, we selected our equipment. So we used the optical sensors, optical cameras instead of infrared cameras to enable more versatile lighting condition. And we selected 4 of the GoPro Hero cameras. These are consumer level cameras, and also the DJI Matrix 600 Pro drone platform. This is the setup of the equipment. You can see this is the camera rig, and on this rig we have 2 cameras facing front and the other 2 cameras facing to the ground. The first step of our technique is to do the camera calibration, where we're going to remove the radical distortion, tangential distortion, and image skew. Then we can estimate the focal length principal points from this calibration process. The next step is the standard stereo rectification. So ideally, in the perfect world, we want the image plane of the left-hand camera and the right-hand side camera to be in the same plane. But in reality, our camera could have inclinations that is making this situation far from the ideal scenario. So what stereo variant rectification does is to bring back the non-ideal situation, convert the non-ideal situation to the perfect situation where the image planes are aligned for both cameras. From that process, we can identify virtual baseline. So that's not the actual baseline between the physical baseline between the 2 cameras, but it's a converted virtual baseline. And also virtual focal length, again, different from the true focal length of the cameras, and also virtual principal point. And also we can obtain an extrinsic matrix. So this matrix is just a transformation of the coordinate from one camera to the other. That allows us to transform the measurement from one camera using the same coordinate system as the reference camera. So here I'm showing the result of the stereo rectification, and you can see after the rectification, the same feature in the left camera and right-hand side camera will be aligned in the same line. So that's the goal of the rectification. After that, we come to our challenging part. How do we calibrate this 2 pairs of the cameras? Essentially, what we need to know is to estimate the relative positions or poses of all cameras. And because our 2 cameras are facing different directions, the same points or same target cannot be visible by all the cameras. So we come up with this 3-dimensional target where we have a vertical plane and a horizontal plane. So we know the 3-dimensional coordinates of the points through the speckle patterns. And then we use that to do the calibration of the two sets of the cameras together. The end result actually is a transformation matrix that is transforming the coordinates of the ROI camera pair to the coordinate of the REF camera pair. So I'm not going to talk about the details about the math, but this is the end result that we're getting. So after that, we're ready to do the measurements. This is the typical stereo vision measurement procedure, where we have two cameras and we have a target. We want to find out the 3D coordinate of this target, and we can use the virtual baseline and the virtual focal length, and also the coordinate in pixels for both of the cameras, and then we can compute X and Y and Z coordinates with respect to this one camera. And then after we computed the coordinate, after we do our transformation, we actually converted the measurement with respect to one of the 4 cameras that is used as the reference camera. So we're using this local coordinate system for our measurement. But we still need to transform this local coordinate system to a global coordinate system to get our true displacement measurement. To do that, we use a stationary target, and then we developed a transformation matrix that transfer the coordinate system from the REF to the global. So the end result is this F matrix. So how we do that, we pick the 5 points on the stationary target and then define the U component, V component, and W component. So after we did all this preparation, we end up with a very elegant process for getting the final result. So we start with the points measured from the ROI cameras and then transform those to the REF coordinates. And then we transform further to the world coordinates. Then we can get the final measurements of the object. And this final measurement of the object is the true motion of the object without the UAS motion, because the UAS motion actually is taken care of by this transformation. So this is the validation results. We first validate our algorithm using stationary points. As you can see, there's several small red dots there. These are on the stationary target, so they are supposed to be stationary, no change with the time. And then we use the hand to move the camera rig to have translational and rotational motion. So you can see we have a fairly large motion in our videos. And then we compare our measurement with the true location of those points. Our measurement have some noise, as of course, and if we compare the RMS error to the ground truth, the errors is below 1 milliliter. Then we build some confidence and we move forward to do a shake table test. So here we have a UAS that is hovering, and then there's one pair of the camera that is looking down at the stationary target, and then we have a concrete specimen that is put on the shake table. Shake table has two. Actually, the shake table has two direction of the motion. And in this case, we did have a speckle pattern on this concrete specimen, but when we're trying to get the result, we compared the result using the bare concrete and the part with the speckle pattern. And what we found is that the result for using natural feature and speckle pattern is similar. So we are sure that we actually can use the natural features for tracking the displacement. And the distance between the concrete specimen and the UAS is about 5 meters. And we also choose a global coordinate system for our final measurements. These are the videos that is taken by the UAS. You can see the fairly obvious motion of the UAS itself. Then we use our algorithm to recover the UAS motion. So these 3 plots are the UAS motion in X, Y, and Z directions. And the figure on the right-hand side is the UAS motion for rotation with respect to X, Y, and Z axis. So you can see a fairly large range of the motion. And then this slide shows the end result for our measurements. The blue dashed line is the ground truth, and the solid line is the measurement that we have. So the RMS error, we have a few milliliter errors for RMS errors. The frequency is preserved pretty well. And for Z direction, actually, we do not have Z direction motion. So the ground truth should be 0, but we do have some noise here. The UAS motion we get is in a range of 215 milliliters, and the rotation is about 5 degrees. So to summarize, this technique allowed us to have the measurement for 3 components of dynamic displacement and 6 components, 6 degrees of freedom for the UAS motion simultaneously. And the error is a few milliliters at the working distance of 5 meters. So to conclude my talk, we presented a particle sensing suite that can be taken to different structures. And we were able to measure all 3 components as opposed to the other existing techniques in the literature, which only measures 2 components in plane or 1 component in depth. The first technique we developed used optical cameras and infrared cameras to measure the in-plane motion and out-of-plane motion, respectively. And the second technique we developed has a mathematically elegant workflow to measure 6 degrees of freedom UAS motion and 3 components of displacement of the object. And also, it's worth to mention that this novel dual stereo vision technology allows longer working distance and versatile sensor orientation. Actually, in our previous technique, we have to have both stationary target and the moving object in the same image plane. And this is very difficult to be achieved in the real world applications. So in our new setting, these 2 cameras can be orientated at arbitrary angles depending on the application. So that makes this methodology much more flexible for field measurement. All right, and the result we presented for this presentation can also be found from these journal papers. And this research is funded by UTC Center from USDOT, and also CSU Drone Center is providing the sensors and the platform. And we also get some student support from Thornton Thermomechanical Foundation. And special thanks go to Dynamics Committee. This committee is so dedicated to help make this presentation opportunity happen. And thank you all for your attention. I will take questions after the next presentation. Thank you.
Thank you so much, Professor Guo, for such a wonderful presentation. So please drop your questions in the chat so that we can address them after our next speaker. So as we wait to hear setting up of Dr. Herta Montoya's presentation, let me introduce you to her. So she is currently an assistant professor at University of Texas at San Antonio. She received her bachelor's degree in civil engineering in 2018. There, she earned her PhD at Purdue University with a concentration in structural engineering and a focus on advancing cyber physical simulation and testing of complex infrastructure systems. She is an expert in dynamical nonlinear systems with multiple degree of freedoms, and she was involved in establishing resilient extraterrestrial habitats for a project sponsored by NASA. And we are delighted to have her today to talk about the thermomechanical real-time habitat simulation and advances and challenges towards creating resilient systems. So please help me in welcome our next speaker. Thank you.
Thank you, Marianne, and thank you to the Dynamics Committee. It's an honor to be here with you today and presenting part of my work. So a part of the work that I'll be presenting today, so I recently completed my PhD. So this is part my PhD dissertation. And a lot of the work was completed at Purdue University, even though I am today at UTSA. So I'll hope that you enjoy the work that I'll be presenting. And it's, as Marianne said, on thermomechanical real-time hybrid simulation and touching a little bit on the advances and challenges that come towards creating resilient systems. So just to start, I'll go ahead and talk about the motivation. So in the last decade, the space community has been committed, as we know, to go out there into space and establish permanent human presence. And right there, I have some of the exploration maps that are available from different identities to go ahead and stay in space. And it is very clear that we are returning to the moon to stay, and that space is the place for innovation and creativity and discovery. And if we go in depth into one of them, for example, here, the one created by NASA, a Moon to Mars strategy, you see that there are very different milestones that have to be accomplished. But in particular, there's one that we need to accomplish before we go farther, which is having a permanent human presence on the moon. And being on the moon and Mars means that we need to work, learn, operate, and sustainably live there for extended periods of time. And right there, here, and I'll get my laser pointer, you see 4 categories where NASA has identified that a lot of the challenges and research areas are available to further this effort. And you can see that having operations, having infrastructure, along with the development of science and transportation and habitation are very important. And big challenges that come with that is that there are unprecedented demands in these extreme environments where you don't have any protection of what is naturally happening out in space. For example, meteorite impacts, of solar flares, radiation storms, and such types of hazards. Also, that you're in total isolation. If something goes wrong, there's no other social infrastructure that can help you out while something goes wrong. And there's limited resources. You can have disruptive conditions from within your system because we're talking about very tightly coupled systems. And for us to look into building the technologies that address these challenges requires us to think about resilience, having smart health management systems, and autonomy. And to test them before we go out in space, we need test and innovation, novel approaches that allow us to bring that stochasticity that we need, not just from numerical models, but also the physical parts that we can have here on Earth. And that's where cyber-physical testing comes into the picture. Now, like I mentioned, a lot of this research was done at Purdue, and Purdue was the leading institution in a much bigger effort, which is the Resilient Extraterrestrial Habitats Institute, which main objective was to enable the technologies needed to establish these space habitats with capabilities that are smart and resilient. And actually, UTSA was one of the partners as well with the University of Connecticut and Harvard. And you can see that their goals align well with this bigger goals shared by the bigger space community. And my role here was to enable a cyber-physical testing technology that could test and validate these groundbreaking technologies needed for smart and resilient space habitat systems. So with that, I'm going to go into what is a real-time hybrid simulation and a little overview. So it is a dynamic testing technique in which a system is partitioned into physical and numerical counterparts. However, it is very important that the interactions and data flow, regardless of how we partition the system, is still occurring so that we can impose a load and still get the overall response of the system. Now, this originated in structural engineering, so I expect most of you to be familiar with it, but it is also known by other names such as cyber-physical testing, pseudodynamic testing, dynamic virtualization, and in some variations, hardware in the loop. And the benefits of this is that you get a realistic evaluation by bringing those uncertainties from real counterparts in the lab and coupling them with numerical simulation, which then gives you a systemic behavior of an overall system rather than just evaluating a small part. And with that, it becomes cost because you don't need to spend a lot of money in building something. Space, you don't need a lot of space to build it, and time effective. So you can move a little bit faster when you're trying to get the systemic behavior of a complex system. And so it has its benefits, and it leverages on the benefits of experimental and numerical modeling. Now, in its general scheme, going a little bit back to structural engineering, if I were to have a building that I want to evaluate under an earthquake load, so a ground acceleration, and I am not able to build it entirely at the lab, however, I want to focus on a specific design that is of interest to me, then I can go ahead and take that part and build it even up to scale in the lab, and that becomes my physical subsystem. Well, I'll have the rest of the building numerically modeled. Now, I still input my ground acceleration that generates a response, and that boundary condition is what I'm going to impose into my physical subsystem. And I do this with the help of actuators, mechanical systems that are able to impose. It could be a mechanical load, or it could be a thermal load. And with sensors, I'm able to measure that response and feed it back into my numerical subsystem. And I do this at every iteration step of the process. So that's what makes it a real-time hybrid simulation. Now, if we go back to the block that I initially showed you, you'll see that there are two additional blocks, which are actuators and sensors, which have their own dynamics as well. So to compensate for that, so that we can have this loading and boundary conditions imposed and shared among the different substructures, we need to do it with high confidence. So we bring in a layer of control. And RTHS has allowed to test larger and more complex dynamic systems, such as the dynamic evaluation of infrastructure. We've heard about it. It's where it originated, and now it is applied to other engineering domains, such as wind turbines and even biomedical specimens. And it's also been used for the testing of structures under fire loads. So it is known as a cyber-physical fire testing. And I proposed a new application for RTHS, which was using it for the evaluation of space habitats, given that they are going to be under extreme loads, and we want to develop the technologies needed to take smart and autonomous decisions. Now, my problem formulation was that I know that we're going to have a lunar habitat or extraterrestrial habitat that will experience extreme temperature variations. And that is having very hot temperatures during the lunar day and chilling conditions during the lunar night. We're talking about 400 degrees Celsius of differences. And even more so, if something happens we need to have a safe performance of these systems. It is necessary that even though we are constantly performing in extreme conditions, if any disruption happens, we still need to ensure that people or systems inside these habitats are safe. And so to study decision making related to such a disruption, like I've just talked about, in such extreme conditions, we need to capture the thermal interactions within a lunar habitat under experiment in these conditions. And so I started out with a prototype, so a conceptual lunar habitat, which is an interior environment that it's going to be covered in lunar regolith. It is great. It has great radiation protection and thermal physical properties to have insulation, to serve as an insulation layer. And I have lunar environmental conditions, and I have this system that is constantly pressurized, and it could be thought of as a structural layer. Now, by you looking at this, it's obvious that I won't be able to replicate the lunar environment condition easily at the lab or in a feasible way. And I don't have lunar regolith available to just, go and cover my structure every time I want to do a test. So obviously this part is going to have to be numerical. While I can build a pressurized system, a pressure box with some structural materials such as steel and aluminum, and I can pressure it at the lab with ease. And so with that, I partitioned it into RTHS components where I'm going to model a lunar regolith layer that's going to serve as a protection exposed to the lunar environment. And I'm going to have a pressure box at the lab. Now, between these two, I'm going to share some interface conditions, and I'm going to measure also to feed it back into the next iteration of the simulation. So one thing, and I don't want to get a lot into the technical details, but obviously the advances and challenges is that I wanted this to be the first RTHS method to experimentally execute the effects of damage and repair with intervention strategies. So more than talking to you about what technique did I use to model this, I want to tell you that I wanted to impose different types of damages. So I wanted to have a model where I could impose uniform damage due to micrometeorite impact or localize it in the case. And why? Because I wanted to allow other researchers that I was working with to develop Bayesian digital twins for fault detection and diagnosis, so that we could answer questions based on what I was imposing at the lab on can we detect damage based on the interior environment temperature, and can we predict the temperature of the habitat after damage so that we can define critical stages. And so with that in mind, I developed the framework where I have a two-way thermal and mechanical coupling between these two subsystems for heating and cooling conditions. So the numerical subsystem was a finite element model. I have there the main equations. It was a heat transient equation for the part that was imposed the thermal loads, and I worked with a quasi-static equation for the deformations of the mechanical subpart. And as you can see here, the mechanical subpart has the forces due to the mechanical events happening, the pressure and other things, but also it has that influence of the thermal stresses for having this varying conditions of temperature that come from the heat transfer model. Now, the heat transfer model had a part of its subsystem being a function of an index of mechanical deformation. So after the impact, the geometry changes, and how does that affect the thermal response? And so these two interacted with each other, and then at the lab there was a physical pressure box that had a pressure management, as you can see right here, and it was the structural system and interior environment represented. Now, I used the thermal actuator, which you can see right here is a cold plate design that could add and impose loads to the surface of this pressure box that was covered with lunar regolith, and there was a control and estimation scheme with this. Now, there were sensors along these components, such as thermocouples and pressure gauges, that will inform my models of the state of the system so that we can carry out the next iteration for the simulation. And of course, each of this had their own loads. For example, the external heat load coming from the environmental conditions of the moon, a myriad impact time, when does the deformations start to occur, and from the experimental part, the set point pressure for such a system, and the pressure heat load from incoming air loads. And so here I'm going to show you a prototype testing result for that lunar habitat. And so everything is happening at the same time, but I'm going to go step by step so that it is not too overwhelming. So there was a numerical subsystem here in the XY plane that had localized deformation, and I impose it and let it run to see what are how that changes the thermal behavior. Then I sent that desired interface temperature to my controller, which then sends that command to a different the actuator and its different components to impose that load. In this case, to bring it down to 270 kelvins. And I was able to build such a controller that I did it with high confidence with a normalized root mean square error of less than 2%. Now, in the system, there were sensors, as I mentioned, such as measuring the entire environment temperature, that were used to then feed it to an estimator that would estimate the heat flux or the heat load that was leaving the system due to having this thermal change. And as you can see, that was always fed back to the numerical subsystem. As you see through time, you can start to localize the damage localize the thermal conditions of that damage, sorry. And so all of this happened at every time step simultaneously, but you can see here some of the components. Now, for validation, we compare the RTHS results to different numerical models, considering different conditions for the interior environment, which was the hardest part to model if you don't do it with a CFD. And so if we assume that there were constant heat transfer parameters, you can see that we were not able to capture it the same way through the different layers that we did it by having that experimental counterpart really actually measuring how the interior environment was reacting to this changing conditions through the structural layers. And as you can see, if we change the conditions, we could maybe fit some of them, as you can see right here, and the interface between the structural layer and the interior environment. If you consider that you're going to have lower convection coefficient between these two boundaries due to having an unbalanced air distribution because the colder conditions are at the top of the pressure box, then we're able to get some of the behavior, but nothing compares to having that physical specimen interacting with the numerical model. So here we showed how it benefit the overall purpose, which was imposing those conditions so that we can test digital twins. Now, moving from prototype to complex system testing, so because we're focusing on system resilience, we wanted to look into a system of systems approach that accounts for disruptions and also the interdependencies among different subsystems. So how fast failures cascade through a lunar habitat. So there were different electromechanical systems that were considered to have this complex system lunar habitat simulator. And as you can see, we include that structural protective layer, the structural system, the interior environment. Now we bring into the framework an environmental control life support system, a power system. And we acknowledge that each of them is going to have certain disruptions and environmental conditions that they're going to have to withstand. And in addition to that, there's a health management system, a communication network that takes those sensor measurements, those cyber interactions, and then can take decisions and do some prognosis and diagnosis. And then an agent can go ahead and impose an intervention into the systems. Now, that led to the development of the cyber physical testbed, which took into consideration all of this parts, and some of the systems were going to be cyber, while others were going to be physically built at the lab, as you see right there, part of the systems that I consider for the prototype. And then the health management subsystem will be tested in its own platform. Now, here I present to you an overview of the architecture of looking how these systems were running at a different machine for numerical simulation, and also the health management running with some telemetry that is shared with what the habitat is experiencing and the physical testbed components commissioned with sensors. Now, where does thermomechanical art teach us played a role in the CPT? Well, here I try to show you in this diagram how the SPL was hosted within the cyber subparts, and then all of the estimation, control, and other technologies developed to impose these interactions between these two systems. You can see them across. And so along with that, we coupled with other physical parts and the health management system, so that, again, I share with you the purpose, enable this technology so that we can test and validate digital twins that are needed for smart and resilient space habitat systems. So I'm going to walk you quickly through a smart hab disruption scenario, which I call this SPL disruption scenario because it meant doing those deformations that I introduced in the prototype testing. So we have a habitat that starts in nominal conditions. Then you have a micrometeorite that impacts your system. It damages your protective layer. You're going to start to experience thermal changes within your structural layer and your interior environment. Then your thermal management is going to try to compensate for those losses. So then increases a demand for power needed for the habitat, bringing it to a critical state. So then we can go ahead and through our health management system, detect the fault, notify the agent, and localize the damage so that the agent can go and do an intervention. Now, after that, we can go ahead and bring the habitat to a repaired state. Now, there are a lot of things that went into play here, but I'll focus on the computational modeling, which was I needed to define a level of damage for these disruption scenarios with a model that had the ability to simulate the damage and also have real-time repair by the health management system, while accounting that I have other faults that are coupling between my systems. Now, in the experimental design, when you're working with the infancy state of digital twins, it is very important that we define damage in a way that it creates effects that are suitable for the training and development of these methods. And so that was one of the challenges and one of the things that I had to consider when thinking of this, and I'm going to briefly go over them. So, for example, I was working with this physical dome. It had 8 thermal panels, as you can see them across the system. The pressurized environment is here, and I had to consider different case considerations. Now, there we go. And so I measured the temperature across these layers for all of these cases, and so my actuator behavior was kind of similar across all this configurations. So I was good in that. But things that you need to consider when working for the development of digital twins is that I needed to impose the lower temperature possibles, which I was able to do that if I have more actuators, thermal actuators imposing thermal loads than not. But I also have to think that I have to localize damage in a way that I am not making something that is not too realistic for the development of these twins. So even though I want to test damage that it's all across that surface, that is not something that is localized. So I'm going to focus on something that is more local. And with that, also, if I localize too much, then I create an unsafe environment for my testing. So I need to also consider those things. So now that I had my SPL and I could do the damage, now I have to do the damage, and I took considerations on damaging my SPL by 75% after a micrometeorite impact. And so with that, then I reduce the thermal insulation of my system. And now comes the HMS and agent intervention. So I want to do a realistic action progression as possible as I can. So if you have remaining material, then you share this with your agent. The agent then has to go through different stages to restore that heat loss. And so it can go adding the thickness by different parts and progressively. And then how fast we do that depends on the agent rate and how it works. So I needed to create a model that took into account that, and also account that the health management system could be interrupted at any moment. And so I was able to do that by using a switch and dynamic model technique, where you can define your different states of the system and switch in between those dynamics by taking in consideration the different inputs of all the systems, so that you can impose those desired temperatures. And then it becomes a function of your repair and your health management and agent. Now here, I'm going to briefly show this disruption results, where you're going to see the different parts that were in play. Here you will see measurements that were actually happening at the lab and the outputs of a health management system. And so I'm going to show only briefly the start. As you can see, we start the simulation, we are sharing data, we are able to create diagnostic outputs of saying, is something good, is something suspect, something's bad, based on this interactions and sharing the data. Then in the system, at a point in time, we damage it, and you're going to see that I'm going to fast forward it, but I need my cursor. So you see through time that we see the power consumption being more frequent, that thermal temperature, interior environment temperature lowering. And so we start to see suspect, then we say we need to repair the SPL, and through time, we get into a recovered state, allowing the agent to, and the digital twins to perform. Now, just to conclude, so Thermomechanical RTHS offers a method where we can do this type of testing with a lower cost, and it's reconfigurable so that we can proceed based on decision-making methods or cascading sequences. And there's nothing compared to real hardware and understanding the stochasticity of physical systems within this platform. And it's of great benefit for the development of technologies such as digital twins. And some possible applications include evaluating large-scale infrastructure under freeze-thaw cycles or extreme conditions, such as bridges and power systems, and assessing the performance of systems on Arctic or deep sea operations. And I want to acknowledge all my colleagues at the Resilient Extraterrestrial Habitats Institute and at Purdue, and also the National Aeronautical Space Administration for supporting this project. Here are some of the references that I had and publications that are already published for this work. And thank you so much for your attention. And if you have questions, I'm more than glad to answer them.
Thank you both speakers for such an engaging talk. We have so many questions, but we do have one question that came from our audience during the talk. And this is a question for Dr. Herta Montoya. David Delgado, would you like me to read your question, or would you like to interact with our speaker today?
My internet maybe is not the best. Maybe you can ask the question, please.
Absolutely. So the question is, are the magnitude of moonquakes significant to be included in your model?
So I'm not the expert on moonquakes. There are actually other people in the institute that are expert on moonquakes. But what I know is that these are, and you probably, due to your question, know as well, that they have very low magnitudes, but they have a long duration. So if you have a pressurized system that is constantly at a low frequency shaking for an hour, it's something that is significant to be included. I focused on thermomechanical interactions, but there's other people that focus on this seismic evaluation of a pressurized system under constant shaking. And so it is something that in the future I envision should be included in such a framework.
Thank you.
Thank
Great
you.
presentation.
So I had a question for Dr. Guo. I was wondering about how are the wind effects accounted when you're looking at this kind of application?
Are you thinking about the wind effects on the UAS system or the wind effects on the structure?
On the UAS system, yes.
Yeah.
Because you were looking at a target and sometimes it's fixed, sometimes it's a moving target. And I was wondering about how are you accounting for the wind effects? Is there a way to do that or?
So are you concerning about the wind effects on the motion of the UAS? Or how? So the UAS is going to have motion due to its vibration itself and wind conditions. And our algorithm can compensate or mirror all the motion of the UAS. So that's not a concern for this technology.
Professor Manolis Chatsis, go ahead.
Thank you both for the presentations. Another question for Yanlin. Yanlin, here, unlike the case of a stationary camera, you have that the camera itself moves on the drone,
Yep.
but also that the pose of the camera keeps changing versus the world frame.
Yeah.
And so in a stationary camera, one would do the pose estimation once. In this case, is the pose estimation repeated frequently, or is there some way around it because of the use of the stationary targets?
Yeah. So since we're tracking the stationary target, the motion of the UAS itself is totally mirrored. However, the assumption underneath is that the camera positions of these 4 cameras with respect to each other is not changing. So we do the calibration one time, and we know that the relative location between the 4 cameras. And that's the assumption. And however, its relative motion to targets or to stationary targets, those do not matter.
Okay, it's re-estimated from the stationary targets. Okay, thank you.
Yeah.
Maybe I can ask the next question if possible. It's also for Professor Zhu. So Professor Zhu, how do you feel about adding more cameras? Would adding more camera system, like 2-3 camera system, increase the resolution or accuracy, do you think?
I think that's fine. So right now, even the stationary stereo vision camera system, you could, if you want to have a higher accuracy, you could have multiple cameras instead of 2, right? So the same concept would also apply in this case. I think our technique, I think the major contribution is that we allow the 2 different sets of the cameras looking at different directions. And that makes the choosing of the reference much more flexible. But the same type of dual stereo vision calibration could be applied in a similar way. I think multiple cameras definitely will help improve the accuracy of the measurements. So right now, the accuracy that you see, the major sources, after we did some other investigation afterwards, we found that the major sources actually is the triangulation errors that you get when you're moving further. So adding more cameras will help in that aspect.
If I may, I have a question for Professor Montoya. So Professor Montoya, can you also comment on the computational demands and needs of this thing, and if this can be on the large scale, can be applied in real time or near real time? Of course, you're doing hybrid simulation.
Yes, so of course, in larger scale, I think for the thermal perspective, it's possible to do it in real time, given that you can have a larger time step So transient heat response is around 1 second. So when it comes to computational demand, it's not too demanding. Sorry for the redundancy, but it's not too demanding. I've worked with a quasi-static response, and I was allowed to work with 1 second time step for that, getting the thermal stresses. It wasn't too demanding, I would say, but if you want to look into a higher order response from the mechanical side, I would say that near real time would be a better approach, or maybe not have it interact at every time step, but have it calculate the stresses maybe every 5-10 time steps to allow you to continue the simulation near real time.
And are there any opportunities for parallelization or like MPI or GPU, CPU-based parallelization processes here?
I would say I didn't get the opportunity to do that, but I do say there's potential, especially with working with structures, because you can kind of separate the elements a little bit more into like segmentation, your beams, your columns, your slabs. In this case, I was working with an entire slab together. So I wasn't able to explore that area, but definitely there's parallelization potential.
Thank you.
Yes. Thank you.
I had a question about how are the damage scenarios determined, and if you had any stakeholder inputs from NASA or in general.
So the damage, it was what I tried to convey was that at the infancy state of the digital twin, I would say that that was the main purpose, to have a damage that was significant for the digital twin to train, while keeping it as realistic as possible. So I'm going to reduce my protective layer and localize it, but maybe I'll need to reduce it more than 50% for me to capture it with my sensor so that I can test if I can localize it. Now, the next step would be what type of damage is the digital twin then able to detect, and we can fine tune that process. But at this moment, it was not so much the stakeholder, but the developer of the digital twin that played a critical role.
That's wonderful. Thank you. So last call for questions for our wonderful speakers. Okay, sounds like we don't have any additional questions, but I want to invite everyone in the audience who's still with us to join us at the EMI conference in Anaheim. And we welcome your contributions. And if there's anyone in the audience who's interested in participating as speakers or joining our committee, you are more than welcome to join. Let's go ahead and also thank our speakers one more time and for their time. And if there's any final words that our speakers can share with the audience. Yeah.
I'll go first. So thank you very much for the opportunity to share my work. I appreciate it. And it's a wonderful effort that you're doing this webinars, because then we can learn a little bit more of what different members are doing, and keep on supporting student presentations, because I was a participant in one of them. I got second place.
I remember
And
that.
yes, and so I always remember that. Thank you.
Dr. Yu?
Yeah, thank you everyone for attending the seminar. I think this committee is doing a great job for making effort to share the knowledge inside the community, and also with our students and our young students. Please be involved more in this committee. Yeah, I think it's very good.
Absolutely. Thank you both for this audience and sharing the knowledge and participating. And these talks are recorded and will be posted in our YouTube channel. So feel free to check that out and share this with your friends and colleagues on these really interesting topics. And now Go ahead and stop the recording now.